So now that we've talked about what it means to be a function defined on a three-dimensional domain and written down a Riemann sum definition for the triple integral, now we would like to have some ways to compute these that don't involve actually computing the Riemann sum, and this is where iterated integrals come in. So in this situation we are still considering our region, our domain in three-dimensional space to be a rectangular prism, so R, that is bounded. So our R will be bounded in the x direction from A to B. Remember, x moves this way, out of your screen as you're looking at this. Our y direction will be bounded between C and D, and our z direction between U and V. And so this rectangular prism can be written as the product of the intervals AB cross CD. Remember, this cross is just the notation for taking the span of everything here. And then in the z direction, UV. And again, suppose that we have some function defined on this region R, which for every point in the region, every point inside, spits out a value, f of p, a real number value, which we can regard as a number in the W domain over here. And so what we would like to do now is remember that the integral, the triple integral of this function f over b, so f of x, y, z, with respect to the volume element. So tiny pieces of this region have small volumes, so we have dv over here. So remember that this is defined by a Riemann sum, but what we would like to do is not have to compute that Riemann sum. Instead, so let me write the Riemann sum. I'm going to write the Riemann sum in pieces now. So this is going to be the limit as, the way I wrote it in the last video, so limit as capital K approaches infinity, sum lowercase k goes from 1 to capital K. I know that's probably a poor choice, but that's what I did in the last video, so let's stick with it. And then the limit as m approaches infinity, j goes from 1 to capital M, and then the limit as n approaches infinity, sum I goes from 1 to capital N of x of our test points. So I'm going to leave off the indexes here. X star, y star, z star, these are just our, well, I'll put them in anyway. Our I, j, k, there's a different test point for every sub-rectangle. Times, then we have delta xi, delta yj, delta zk. And this is our Riemann sum definition with the limits distributed to the sums. And what we want to do now is write this out as a iterated integral. That's our goal here, iterated integral, just like with our double integrals. So the first integral is just going to be the integral from a to b in the x direction of our function f of x, y, z, dx. Of course. So just treating this like in other words, ignoring everything outside and just treating this like a function of only x, we can integrate this up in the Calc 1 sense with respect to just x, treat y and z like constants, and then we can do the same thing as we move outward. All right, so the next integral will be the integral from c to d of this whole scenario, dy, and then finally the integral in the z direction is the integral from u to v of the output of, so these two integrals on the inside have already been computed, dz, and this is called an iterated integral. It's just like our two-dimensional iterated integrals, and again the way that it works is from inside out. So you compute the innermost integral first and you work your way out. Okay, this is going to make it much easier for us to compute. This only works when our region is a rectangular prism. I wrote B here. Up here I meant to write B as well. So B for box, right? R for rectangle for the two-dimensional regions, B for box for these three-dimensional regions. This iterated integral only works, like I said, this definition only works the way it's written here with these constant limits in the integral when the region is a rectangular prism or box. Okay, well, I've written up here in the title of the video that this is videos about iterated integrals and Fubini's theorem. Okay, so let's remember what Fubini says. Here's our theorem. For two-dimensional integrals, or double integrals I should say, Fubini's theorem says that we can change the order of integration if we're integrating a nice function over a rectangle. And the same situation is going to be here. So let's suppose that w equals f of x, y, z is a continuous function. So let's say it's continuous on a box. I'll just keep calling this a box now so I get the letter right. So box B for box. On a box B that is obviously defined to be the product of three intervals. So this function is continuous on this box. Then Fubini's theorem says that the triple integral of this function over this box with respect to the volume element can be computed in a whole bunch of different ways. So now we could do it exactly the way we wrote it before. Integral from a to b first, f of x, y, z dx. Then take the integral from c to d, dy, and then from u to v, dz. And now because there's three dimensions here, three different differentials out here, there are actually 6 different orders that we can write this integral, and Fubini's theorem says that all of them are acceptable. So I'm going to write down maybe 2 more of them and leave the other 3 for you guys. So one thing we could do is just switch the order of the inner integrals, and obviously if you switch the integral symbols here, you have to switch the differentials over here. The differentials actually rule. So the idea is here you're switching the differentials, you have to switch the limits. And this integral will then say that the outer integrals from u to v, the next innermost is a to b, and the innermost is c to d, f of x, y, z, and the differential order over here is dy, dx, dz. Okay, and then, like I said, I'll write one more. There's actually 4 more, but we could switch these outer ones. Obviously, again, if you're switching here, you switch both the differentials and the limits. And so this is also equal to outermost c to d, next innermost ab, innermost uv, f of x, y, z. This time the order of the differentials is dz, dx, dy. So, as an exercise, there are 3 more of these. So write down the other 3 that are acceptable. So Fubini's theorem tells us that we can do any of these orders. So if we want to compute this for a continuous function over a rectangular prism, we can change the order of integration to be whatever we want. And really the way we should be thinking of this is that we can change the order of the differentials on this side. The consequence is that you have to have the proper limits in the integrals on symbols on this side. But the orders are these. All right, so even though I've told you to do this as an exercise, let's write them all down. So dv could equal dx, dy, dz. Let's write down the ones we had. It could be dy, dx, dz. It could be dz, dx, dy. What are the other orders? Well, it could be dx, dy, dz. So it could be any of these, right? Oops, dx, dy, dz is the one we already have. So dx, dz, dy. Okay, it could be dy, dz, dx. And then the only one that's missing is dz, dy, dx. Okay, so these are the 6 different acceptable orders of the differentials dv, and again, when you use these to integrate, you have to appropriately change the order of the limits on the left-hand side of the integral. But these are the 6 different acceptable orders of the multiplication of the differentials in the dv, the volume element.